Let's investigate quantum teleportation. Consider two scientists called Alice and Bob. Alice wants to teleport a qubit from her lab to Bob's lab. In this video, we're going to analyze a quantum circuit which describes the procedure for quantum teleportation. This procedure begins with 3 qubits. Alice is responsible for qubit 1 and qubit 2. Bob is responsible for qubit 3. Let's see how Alice and Bob are going to initialize their qubits. Alice will initialize qubit 1 in the general state psi. This general state psi is the qubit state that she wants to teleport. So we will begin with this state in Alice's lab, and after the quantum teleportation procedure has been completed, this state will appear in Bob's lab. Alice also needs to initialize qubit 2 in the state 0, and Bob needs to initialize qubit 3 in the state 0 as well. This 0 is a label for this ket. It is one of the computational basis states for a qubit system. And this state psi is an arbitrary general state which can be expressed as a linear combination of 0 and 1. And we're going to call the coefficients in that linear combination alpha and beta. So this is how we're going to initialize the 3 qubits. The next step after initialization is going to be to entangle qubit 2 and qubit 3. We're going to turn this 2-qubit computational basis state, 0, 0, into a Bell state. And we can do that by applying the Hadamard gate, followed by the controlled NOT gate. And this is the symbol for the controlled NOT gate. This is the symbol for the Hadamard gate. So I'll draw a line going here and over here, and another line going here and here. These single lines represent qubits, and those qubits are moving through time. So from left to right, that is the convention that time flows. And this qubit up here, which is initialized in the state psi, this is just going to remain unchanged for now. But we will be changing it later. Now, I'm actually going to cut over here, and we're going to see what is happening at this stage in the quantum circuit. So I'll draw a little line. So this stage over here, we can label this stage by the state psi 1. So what is psi 1? We will see that psi 1 can be written as the tensor product of this state psi with the Bell state that is generated by this part of the quantum circuit. So this Hadamard and controlled NOT, they are used to entangle these 2 qubits. Now, at the end of this process over here, we have produced an entangled state, and it is actually a maximally entangled state. So the next part of this procedure involves another controlled NOT, and the controlled NOT is going to be over here. So we have a controlled NOT gate, and we're going to take this qubit and this qubit, and they're going to be involved in this controlled NOT. So this dot represents the control, and this target represents the target. For this controlled NOT gate, qubit 2 is acting as the control, and qubit 3 is acting as the target. For this controlled NOT gate, qubit 1 is acting as the control, and qubit 2 is acting as the target. And over here, we're not going to have anything happening to Bob's qubit. So Bob is responsible for this 3rd qubit over here. And again, I'm going to draw a little line, and we're going to see what is going on at this stage after we apply this controlled NOT. And we'll call the state over here psi 2. Then the next step is going to be to apply another Hadamard gate. And the Hadamard is going to be applied up here on qubit 1. So this H denotes the Hadamard gate. So we'll connect up this qubit, and these qubits are going to remain unchanged. So it's equivalent to just having the identity operator over here. And again, we will draw a little line, and this line is going to specify a state at this stage in the quantum circuit. And we can call this psi 3. That's going to be the name for the state at this stage. After this stage, Alice is responsible for these two qubits, qubit 1 and qubit 2. And she's going to measure both of those qubits. And the measurement gate has this symbol. So this is like a little dial over here. We are performing a measurement. So these two qubits are going to get measured. And a qubit is going to go in, and when we perform the measurement, this qubit is going to collapse to a bit. And in these circuit diagrams, we denote a bit, a classical bit, by a double line. So we're going to have a double line over here. And this double line is actually going to be used to construct a controlled NOT gate over here. So we're going to have controlled NOT again. But notice that we have a double line. This is not a single line. For the single lines over here, those are visual depictions of qubits. So all of this stuff over here, we're dealing with qubits. But once we perform the measurement, the qubit disappears and it becomes a classical bit. And we also have a similar situation over here. This is another classical bit. And we're going to use that to construct a controlled Z, or controlled phase gate. And that is going to go down here. So this is Bob's qubit, qubit 3 at the bottom. And Bob is going to need to apply these gates depending on the results of the measurement. So we'll complete this line over here. And we can also complete these double lines all the way to the end over here. So these double lines represent classical bits, and these single lines all represent qubits. And this over here is a controlled X gate, and this is a controlled Z gate. So you can think of this as a bit flip and a phase flip. And Bob needs to apply the bit flip and the phase flip depending on the results of these measurements. And at the end over here, this state is going to be psi. So that is the same psi that we began with over here. So Alice initializes qubit 1 in the state psi, and at the end of this procedure, Bob is going to get qubit 3 to have the exact same state. But you can see that Alice is going to lose that state psi. So in the process of teleportation, Alice loses this state, and it goes over to Bob's lab. This is actually a consequence of the no cloning theorem. In quantum mechanics, you cannot just make copies of quantum states, but you can teleport states. So this is permitted. You can teleport states from one lab to another, but you can't make two copies from a single state. So that is known as the no cloning theorem. Let's examine all of the possibilities of these measurements over here. So what are the possible outcomes? There are 4 possible outcomes that Alice could get when she performs these measurements. So let's write them down over here. First up, we will have 0, 0. Then we will have 0, 1, 1, 0, and 1, 1. So if the results of these measurements are 0, 0, then Alice will communicate that information through a classical channel over to Bob's lab. And then Bob will realize that he does not need to apply any of these gates over here. And that's equivalent to applying the identity. And we can rewrite the identity as a product of Z and X, both raised to the power of 0. Now you might think this is a little redundant. We're not applying the bit flip and we're not applying the phase flip. So we're raising it to the power of 0. That's the same as not applying it. But this notation is actually very convenient when we write out the other cases over here. So for this case, 0, 1, what does that mean? Here we have 0 and here we have 1. That means we don't apply this Z, but we do apply this X. So the bit flip gets applied. That means we can just write X over here. And this can be written as Z to the power of 0 and X to the power of 1. You can see that these exponents are the same as the results of this measurement. And what about this case over here, where we swap the 1 and the 0? So this corresponds to a 1 over here and a 0 over here. So we don't apply the bit flip, but we do apply the phase flip. We can write that as Pauli z. And this is the same as z to the power of 1, x to the power of 0. What if both of these outcomes are 1? What if we get 1, 1 over here? Then we have to apply both of these gates. But the order is important. Notice that time flows from left to right by convention in this quantum circuit. That means we first apply x and then we apply z. The bit flip comes first and then the phase flip comes. So that means we have to apply zx like this. That's equivalent to z to the power of 1 and x to the power of 1. But why is this in the opposite order to what we see in the quantum circuit diagram? That's because when we apply matrices, this is matrix multiplication, we have to write it in this order. So the one that's furthest to the right gets applied to the state first. So first we apply x, and then we apply z. But over here, we're doing the same thing. We're just representing it using a different convention, where time flows from left to right. You could also use the opposite convention, and then you would have to invert this entire quantum circuit. But the standard convention that is used around the world is this convention, where we go from left to right. So these over here are the corrections that Bob has to apply given the results of Alice's experiment. Now, the next thing that we're going to do is we're going to carefully analyze what is happening to the state of this 3-qubit system as we progress through the quantum circuit. Let's begin by writing down this state over here. So what is psi1? Psi1 is the tensor product of this state psi, when we're trying to teleport, and the result of this combination over here. And this combination of the Hadamard and the controlled knot produces a Bell state. And we can label that Bell state as beta 0, 0. So let's write this out in a more expanded form. So psi can be expressed as a linear combination, alpha 0 plus beta 1. And what about this Bell state? Well, this Bell state it takes in the input 0, 0, and it spits out 1 over the square root of 0, 0 plus 1, 1. So this is the Bell state that we can construct by applying the Hadamard and then the controlled knot to this computational basis state. So if we ignore qubit 1 for a moment, we just look at this and we can treat this as a 2-qubit system. 0, 0 is one of the 2-qubit computational basis states. And it will get mapped to this Bell state when it passes through this quantum circuit over here. So this is the quantum circuit that is used to construct Bell states from 2-qubit computational basis states. So this tensor product over here of a general state, psi, with the Bell state can be written alternatively. We can write it as 1 over the square root of 2 times alpha. We have 0, 0, 0. That's 3 zeros. Plus alpha 0, 1, 1. 0, 1, 1. And then we're going to have beta 1, 0, 0. And beta 1, 1, 1. So that's 3 ones. So this is the state psi1. We've expressed it in terms of these kets over here. And these kets, this is shorthand notation for the tensor product of all of these computational basis states. Next, let's have a look at what happens at psi2. So what is psi2? Psi2 is the result of applying a C0 gate to psi1. So you see this state over here, psi1, gets acted on by this controlled knot. And qubit 1 is the control, qubit 2 is the target. And when we evaluate this, we're going to get psi2. That is the state at this stage in the quantum circuit. So we can write this as 1 over the square root of 2 times, let's see what happens to each of these states over here. So we're looking for states that have 1 in the beginning. So the first bit needs to be 1. And this is going to activate the controlled NOT gate. And when the controlled NOT gate gets activated, it flips zeros and ones and the second position. So this second bit is going to get flipped. So these first two are going to remain unchanged because there's a 0 and a 0 in the first position. So we can write those states as 0, 0, 0 plus alpha 0, 1, 1 plus beta. And over here, we get activated. So this is 1, 1, 0. So you can see this 0 has now turned to a 1. And then we're going to get 1, 0, 1. 1, 0, 1. So this first bit activates the controlled NOT gate, and that causes a bit flip to occur at the second bit. So here we have a 0 turning into a 1, and a 1 turning into a 0. And we can close the bracket over here. So this is the result of applying the controlled NOT gate. Now let's see what happens when we apply the Hadamard gate to the first qubit. So the result of that is going to give us psi 3. So psi 3 is the same as the Hadamard, which I'll put a little subscript 1, so we know we're acting on the first qubit, on qubit 1, and that is acting on the state psi 2. So you can see similar procedure to what we had over here. For psi 1, we define it this way, then we act with the controlled NOT gate, and that gives us psi 2. Then we take psi 2 and act with the Hadamard gate, and that's going to give us psi 3. So that is the state of this 3-qubit system at this stage in the quantum circuit. So this is equal to 1 over the square root of 2, and we're going to have a lot of terms expanding and popping out over here. So what we need to do is consider the first qubit over here. So the zeros and the ones in the beginning. The Hadamard gate is going to turn them into a superposition of zeros and ones. If we have a 0, then we're going to get 0 plus 1. And if we have a 1, we're going to get 0 minus 1. That is the definition of the Hadamard gate. That's how the Hadamard gate acts on single qubit states. So let's see what happens. We're going to have alpha on the square root of 2. There's a normalization coefficient. And we're going to have 0 plus 1. So that is coming from this 0 over here. And then we also have these two zeros. And we can write them as 0, 0. Then we're going to have alpha on the square root of 2 again. And this 0 is again going to turn into 0 plus 1. And over here we have 1, 1. So that is 1, 1 at that location. And then we have to look at these beta terms. So that's going to be plus beta on the square root of 2. But now we have ones over here. So instead of a plus sign, we're going to have a minus sign. So that is the state 0 minus the state 1. And that is followed by 1, 0. So we have 1, 0 over here. And finally, we're going to have beta over the square root of 2 times 0 minus 1, and it is followed by 0, 1. So that's 0, 1. And we can close the bracket over here. So can you see what has happened? This Hadamard has acted on the first qubit in all of these states. When there is a 0, it has expanded it out into a superposition of 0 plus 1. And when there is a 1, it's expanded it into a superposition of 0 minus 1. And everywhere we have introduced a normalization factor of 1 over the square root of 2. Next, let's group these guys together and actually expand this out so we can see some more patterns. Because when we analyze this, we're going to see some very interesting patterns. So I'll write that underneath over here. We can notice that this 1 on root 2 is going to multiply with all of these 1 on root 2s, and we can pull out a common factor of 1/2. So 1/2 multiplies everything. We can also notice that there's a common alpha over here. So we can write this as alpha times all of these states over here. So first we're going to have 0, 0, 0. That's 3 zeros. Then we're going to have 1, 0, 0. 1, 0, 0. And from over here, we're going to get 0, 1, 1. And then we're going to have 1, 1, 1. 1, 1, 1. So you can see all I'm doing is taking the tensor product. So I'm combining these guys together. So this 0 over here could have been written as a separate ket. And then we expanded that out when the Hadamard gate acted on it. So you can see that this 0 combines with these two zeros. This 1 combines with those two zeros. And over here, the 0 combines with those two 1s, and the 1 combines with those two 1s. Now we can close the bracket, because that's all the terms that have an alpha out the front. Now let's have a look at the terms that have a beta out the front. And let's write them down. So first we have 0, 1, 0. 0, 1, 0. Then we have minus 1, 1, 0. And then we look over here, we get 0, 0, 1. That's 0, 0, 1. And then we have minus 1, 0, 1. And we can close the bracket for this beta, and we can also close the bracket for the 1/2. So this 1/2 multiplies everything. This beta multiplies these 4 terms, and this alpha multiplies these 4 terms. So now we are ready for the final step. We can consider the result of measuring these two first qubits. So qubit 1 and qubit 2. So we're going to factor out the result of that measurement. We're going to factor out all the terms that start with 0, 0, 0, 1, 1, 0, and 1, 1. And then we're going to see what remains. So let's do that underneath. What we're going to get is 1/2 times, first, let's consider all the terms that start with 0, 0. So we have 0, 0, and we can actually write this as 0, 0 and collect up all the terms. That's going to give us alpha 0 plus beta 1. And I'll show you where those terms came from. So imagine you take this term over here, you can pull out the first two zeros, and then you just have a alpha multiplying 0. And if you look over here, we have a term that has 2 zeros in the start, and then 1. And this is multiplied by beta. So that is where this term has come from. We have 3 more of these terms, so we can consider the term 0, 1 next. And 0, 1 has the terms alpha 1 plus beta 0. So you can see what's happened over here. We've swapped the 1 and the 0. Where have these terms come from? Well, there is a 0, 1 term over here, and there is a 1 following that. So we have 0, 1, 1. And then what about this term with the beta? Well, there is a 0, 1 followed by a 0. So that explains this term over here. We have 0, 1, 0. Now there's 2 more terms. Let's have a look at the 1, 0 term. The 1, 0 term has alpha multiplying 0 minus beta multiplying 1. Now, can you see where those terms have come from? We can see a 1, 0 term over here. So 1, 0 is being multiplied by alpha, and there is a 0, so that's this. And what about this term? We have a 1, 0 over here, and that's going to give us a minus beta times the state 1. So we can pull this 1, 0 out the front. And finally, let's have a look at the 1, 1 terms. So the 1, 1 terms are going to have alpha 1 minus beta 0. And we can close the bracket over here. That's this bracket, and we also close the bracket for the 1/2. So 1/2 is multiplying all of these terms. We have a bracket for this, bracket for that, another bracket here, and a bracket over here, and this is the final bracket for the whole thing. So where did these 2 terms come from? Well, we can see 1, 1 over here, and we have 1, 1, 1. So that's alpha times 1. And what about over here? Here we have 1, 1, and 0. So that explains this 0, and it also explains this minus beta. There's a minus sign over here. Now, what I'm going to do is I'm going to write this in an even more condensed form. We're going to have 1/2 times the state 0, 0. This is the same as the identity acting on the state psi. This is the original state psi that we started with. You can see this is psi unpacked. It is written as a linear combination of the computational basis states. Then we have the state 0, 1, and this is the result of a bit flip. You can see that the 0 and the 1 are swapped. So we can write this as x times psi. That's the bit flip acting on the state psi. And then we have 1, 0. That's this state over here. This is the result of a phase flip. So the phase flip is Pauli Z acting on psi. And what about this over here? This is not just a phase flip or a bit flip. It's a combination of both. So we have the state 1, 1, and then in brackets we can put the result over here. So you can see that there is a minus sign. So that means a phase flip has taken place. But then after that phase flip, we have these guys swapped around. So the 1 has turned into a 0, and the 0 has turned into 1. So we can write this as x followed by z. Now the order is very important, because if you swap the order, it also swaps the sign. So we will discuss this in a moment. So we have this final bracket which closes this. So 1/2 is the coefficient for all of these values. 1/2 is not the probability. You have to take the square of this coefficient to give you the probability. So the square of 1/2 is a quarter. The probability of getting any of these 4 outcomes is 1/4. So what is going on here? We have the state on the right, which is what Bob has. So this is the qubit that Bob is dealing with, the state over here. So at this stage over here, where the green line is, that is what this blue line is describing. Psi 3 is this state. So after this stage, if Alice performs her measurements on qubit 1 and qubit 2, she will get those 2 outcomes, the outcomes that we discussed over here. Then she has to go through a classical channel and send that information to Bob. When Bob receives that information, he can apply a bit flip or a phase flip or a combination of both. And that is going to fix up his state and make it the same state that Alice began with. So this is Alice's starting state that she initialized in her lab, and this is the same state teleported over to Bob's lab. This is quantum teleportation. And you can see that this over here tells you what Bob needs to do to fix up his state. So if the result of Alice's measurements are 0, 0, 0, then we're going to get the identity acting on psi. And if the identity acts on psi, then that Bob actually doesn't have to do anything. Bob can just leave the state alone, and he has successfully contributed to this quantum teleportation procedure. But if the results are different, Bob has to do modifications. This x over here can be undone by doing another bit flip. So x is its own inverse. The identity is also its own inverse, and Pauli Z is its own inverse. They are Hermitian and they are unitary. So a bit flip is undone by another bit flip, and a phase flip is undone by another phase flip. So these guys can just be undone by x and z. But you can see that the opposite order is present over here. Here we have xz, and over here we have zx. Why is that the case? Well, I'll write this out explicitly. If you have zx, and then you apply the state xz, this is equivalent to z times xx, so that's x squared, z, and this is the same as the identity. So we have z, z. This disappears because it's the identity. And here now we have z squared, and z squared is equal to the identity as well. So you can see that applying this and this undoes the action of this first guy over here. So we have xz acting on the state, and then what we do is we act on that state with zx. And that gets us back to the identity acting on that state. So we can recover the original state. Another way of looking at it, I'll write that over here, is if you take the Hermitian adjoint of xz, this Hermitian adjoint is equal to z Hermitian adjoint, x Hermitian adjoint. And because these Pauli matrices are Hermitian, this is the same as zx. So the inverse operation of this combination is just swapping the order. Because these guys are Hermitian, the Hermitian adjoint is not needed. We just have to swap the order of these matrices. And another interesting point is that when you multiply these guys together, it is equivalent to the Pauli Y matrix, up to a constant of plus or minus I, depending on the order. So this can also be written in terms of the Pauli Y matrix. We just have to keep in mind that there is always a coefficient of plus or minus I. So the order swaps the sign. That is very important to remember. Overall, what have we done in this video? We have shown a quantum circuit that describes the procedure required for quantum teleportation. If we follow the procedure over here, we can see that Alice will be able to teleport an arbitrary general qubit state from her lab to Bob's lab. We have seen what happens at very important stages in this quantum teleportation procedure. We have written out the states explicitly, and we have seen what happens when we take this measurement over here. That actually collapses to one of these four possibilities, and then Alice has to send the results of those measurements to Bob, and Bob can fix up the state that he has so that it matches the original state that Alice had. We will talk more about quantum teleportation in later videos.